All right, how's everybody doing? Professor Brian back. This will be part 2 of our Workout Wednesday on the Chapter 7 in-class worksheet. So we're going to be doing the second half of the worksheet. The first half over Lewis Structures and Molecular Geometry has been posted as well, so go check that out if you haven't. Question 2 starts to talk a little bit about determining molecular geometry around a larger molecule. So up until this point, we've really focused on molecules with one central atom. However, this same concept applies as we start to build bigger and bigger molecules. And from a practical standpoint, realistically, most of our molecules that we deal with in chemistry in a laboratory setting are going to be molecules that are a little or much larger. So here we have a molecule that is probably familiar to some of you all in the biological realm, but it is an amino acid. Essentially, it may not necessarily be one that you're familiar with yet, but as you move forward in your biochemical coursework, you will see this. We have an acid group, an amine group, a sulfur group, and the carbons that connect them. Remember, each single line in any of these, right, is a single bond. Any double lines is a double bond, and any lone pairs obviously denote a electron domain that is a lone pair. Okay, but that's not what the question is asking. The question is asking us about molecular geometry around each of these atoms that are carbon, sulfur, nitrogen, and or oxygen. So let's just label first off the carbons because we have more than one of them. So 1, 2, 3, 4, 5. Okay, we have one oxygen that we're interested in, or we can label both of them, 1 and 2. And then sulfur and nitrogen, we only have one of each. So let's talk about carbon 1. So carbon 1 has 4 bonding domains. We should be at this point, without having to go to our chart, but I'll go to it really quickly. Whenever there's 4 bonding domains, tetrahedral, we need to be able to immediately recognize that prior to our next assessment. So 4 bonding domains, tetrahedral. If we notice, carbons 2, carbon 3, and carbon 4 are all the same. They have all 4 bonding domains, no lone pairs. They are all tetrahedral. However, carbon 5 is not. Carbon 5 only has 3 bonding domains. And when there are 3 bonding domains and no lone pairs, we are dealing with trigonal planar. Again, you can verify this using your Vesper chart if you need to. Pause, go take a look at it, and verify it. Now, we have 2 oxygens we need to look at. So oxygen 1 and oxygen 2. Oxygen 1 has 4 electron domains, but only 2 bonding domains, but 4 electron domains. Whenever we have 4 and 2, we can look at our chart and we can recognize that 4 and 2 gives us bent. Usually angles are less than 109.5 due to lone pairs. So we would expect oxygen 1 to be bent. And oxygen 2 doesn't really have electron geometry around it because it's only connected to one thing. So effectively, it has 1 bonding domain, and it would be linear if I was to ask you that, right? 1 electron domain as well. But that's not really an important one. Mostly we're talking about atoms that are connected to more than one. Okay, if we want to talk nitrogen, nitrogen has 4 electron domains, but only 3 bonding domains. Now, we haven't seen this one in this molecule yet, but if we go look for 4 with 3 bonding domains, we see trigonal pyramidal. So we now have 4 different ones: trigonal planar, tetrahedral, bent, linear, and trigonal pyramid. We have 5 different ones. And then last but not least, We can use purple. Sulfur has 2 bonding domains with 4 electron domains, and we should recognize that that is bent, similar to how we see our oxygen number 1. So this is a great example. A question like this will very likely be on the assessment in the midterm. Can you determine molecular geometry in a expanded larger molecule, not just a basic Lewis structure? Now, you won't be asked to draw anything like this. You will be given this and be asked to then assess its molecular geometry. So let's talk a little bit conceptual work. What determines whether a bond is considered polar, and what determines if a molecule is polar? Well, bond polarity, simply put, is equal to a difference in electronegativity between 2 atoms, and we could say 2 bonded atoms, better stated, that is larger than 0.5 from the Pauling scale. And again, you will be given these values. Remember, these values we generally see as listed whole and a tenth integer values, a whole and tenth numerical values, and you will be given those if necessary. But if the difference is larger than 0.5, then we expect for a bond to be considered polar. This means that electron density exists in one area more than it does in the other. And for a molecule to be polar, molecular polarity means a net, keyword there, net dipole exists. Okay, this just means that the sum of the bond dipoles gives us a net dipole that is non-zero. Okay, that is non-zero, and we've seen this in plenty of examples of videos, and I've shown that as well. And here's an example for us, essentially right behind that. If we look at HCCl3, (7, 14, 21, 25, 26), the correct Lewis structure here in 2-dimensional format has 3 chlorines and 1 hydrogen bonded to a central carbon due to carbon's lower electronegativity. And we can go to our electronegativity chart and see that carbon is 2.5, chlorine at 3.0 does give us what we need, a 0.5 difference, to essentially expect for there to be a bond dipole. Now, when we talk about carbon hydrogen, we also should recognize that carbon and hydrogen is very close to one another and does not give us enough to show a bond dipole in that area. What do these bond dipoles create? They create partial negative charges around the chlorine and a partial positive charge near the carbon. Now, molecular geometry tells us that this molecule is better represented as a tetrahedral geometry, which would give us a wedge and a dash. And these bond dipoles would add together to give us a net dipole. And that net dipole would be down away from the carbon in between the 3 chlorines, because this is a tetrahedral molecule. Now, this is a good example to talk about why this VSEPR chart needs to be read very carefully. If we look at the tetrahedral portion of this chart here, it shows you that 4 bonds, tetrahedral geometry, but it also shows you nonpolar. The reason why we must be careful and read what it says molecules with this shape are nonpolar when all of the atoms are the same. If the atoms connected to the central atom are different, the molecular polarity needs to be considered on a case-by-case basis. This is that example. HCCl3 is polar even though it's tetrahedral because all of the atoms are not the same. The net dipole exists because the bond dipoles do not cancel. Remember, this is still going to give us the bond angles of 109.5. However, the bond dipole for the three chlorines will add together to give us a net dipole. So be aware of that and understand that this kind of question will likely come up, and you will need to be able to differentiate between a tetrahedral molecule that is and is not polar. Okay. So let's talk hybridization. Okay. We don't talk much about silicon, but in some instances we do see silicon create what we call covalent compounds. It is generally considered a metalloid, which means it has characteristics of both. So I'm going to move to some notebook paper to give me a little bit more space to talk about this silicon tetrahydride. So from a valence electron perspective, we're looking at 4 plus 1 plus 1 plus 1 plus 1, which is a total of 8 valence electrons. Silicon is the central atom. Easy to figure out here because we're dealing with hydrogen. Obviously, hydrogen can only create that one bond. Now, we've used our 8 valence electrons, and we have what we should at this point be extremely comfortable and quick to recognize that this is tetrahedral. Okay, we have 4 electron domains, 4 bonding domains. We have all single bonds. Okay, but the question, if we remember, is asking us about the hybridization of the central atom. So we can take a look at our Vesper chart and get some insight into hybridization. If we go and see that there are 4 bonds and we have tetrahedral geometry, notice that it tells us the hybridization in this chart. You won't have this chart, but using it for all of your work and homework leading up to the assessment will give you a better understanding so that you can immediately recognize that this is sp3. Okay, 1s orbital, or it's specifically, this is the 3s orbital of silicon and the 3px, 3py, and 3pz orbital all coming together and hybridizing to create what I've shown in previous videos as what we call sp3 hybridization, okay, where the central atom is hybridized. Now, you need to be able to recognize that. You also need to be able to show and recognize that each one of these hybrid orbitals in this example are bonded to that hydrogen, and these are sigma bonds. So we do have 4 sigma bonds. So that's also something that we need to be comfortable in recognizing. Okay, the next example is in I3. So in I3, valence electron 5 plus 7 plus 7 plus 7 equals 26. Nitrogen being the central atom with 1 lone pair and octet fulfillment on all of the iodines via lone pairs as well. Uses up our 26 electrons, and we have a molecule. Now, molecular geometry, we got to be comfortable at this point to see that this is trigonal pyramidal. And if we go to our Vesper chart, we see that we have 4 electron domains with 3 bonding domains. This is different from a tetrahedral molecular geometry. This is trigonal pyramidal molecular geometry. However, we see that the hybridization is in fact the same. So here we are dealing with sp3 hybridization of the 2s and the 2px, 2py, 2pz coming together to create the exact same situation that we saw before, except now instead of 4 sigma bonds, we now have a lone pair in one of the hybridized orbitals, and we have 3 sigma bonds occurring around this central nitrogen. So we are still dealing with a single sigma bond, but we are only dealing with 3 of them. So you need to be able to recognize hybridization as well as recognize the number of sigma bonds. We also should be able to recognize that this is going to be less than 109.5 due to the lone pair being there. And the last example, if I'm not mistaken, is CO2. And now we can talk about a molecule with multiple bonds. So CO2 has the valence electrons of 4 plus 6 plus 6 equals 16. Carbon central. And oxygen's electronegativity builds us this molecule first. We then create double bonds, and we find ourselves with the final Lewis structure. All right, and each of these was from the creation of a double bond. Now, this is a linear molecule from a geometric standpoint, which means that we are dealing with 2 electron domains and 2 bonding domains. If we go to our VSEPR chart, we see that the hybridization on a 3-atom linear molecule is in fact sp. So we have taken the 2s and the 2p, let's call it x, but it can be any of these axes, right? If we think about axes in this format, right? The atoms are in one of the axes. You can call them x, y, or z. For this purpose, I'll just call this x, z, and then we can call that the y-axis. So the z and the y p orbitals are not being used to create the sp hybridization. Notice we only have one, only have p. We still have left over pz, excuse me, and py. They're still left over, okay? And that's going to be important because if I was to draw the orbital overlap for you, and I'm going to try to use the same colors. Let's see if I can accomplish that here. The carbon sp orbital diagram, if carbon was in the center, would look like 2 lobes that are in fact 180 degrees in bond angle, and we can find that on our VSEPR chart. But we have left ourselves with the p x and pz, which are left over, and these are 90 degrees from one another, and we should be able to recognize that. So if I was to show these and their bonding to these oxygen, we would actually find that the oxygen atoms are also hybridized, okay, particularly in sp2 hybridization. And I'm going to try to draw this, keeping in mind that my colors are showing the sigma bond of oxygen, right? So I'll just write the O in the center there. And this represents sigma bonds. However, we're not done, right? This is the sigma bond. We're not done because the leftover p orbitals that I spoke about for carbon, and again, these would have in the page and out of the page, those leftover p orbitals also exist for the oxygen. If we remember, sp2 only uses 2. What we would actually have is we would have interaction between these two, creating a pi bond for us, in interaction, let's say, between these two, also creating a pi bond. And this is not the greatest diagram. If you see my other videos, I've shown some better diagrams. And just to keep it clear, this is the sigma bond with the head-on overlap of the hybridized orbitals. And this is just based upon our hybridization. We will talk further about molecular orbital theory, which gets a little more specific about that. But this would be sp hybridization and a little bit of the bond orbital overlap diagram for CO2 using that. So we have 2 pi bonds and 2 sigma bonds, creating 4 bonds around our central carbon atom. And so what I've done via question 5 is I've actually answered question 6 for us, the 3D representation here. And however, I will give you a little bit better description when we're talking about pi bonding. Okay, and I was showing this situation, and we'll use that same molecule. The interaction is not just a line, right? I drew a line here to show interaction, but the three-dimensional representation of the electronic density that exists there, and I'm going to use green, but I'm going to use a lighter color, is actually like a electron cloud that exists. Essentially what we call the delocalization of electrons. It exists in and between these orbitals that we are familiar with. So we could have electron density in any part of where I have kind of shaded this green. Okay, and that's important for us to recognize. This is what the pi bond looks like from a three-dimensional standpoint if we talk about it mathematically. Now, when we utilize sigma in the notebook, and I used red and purple, so I'll make sure I use the same one. The overlap for the red and purple from sp2, that overlap is very similar, but that the electron density is still electron density, but it's only where these bonds overlap, not in the space in between them, similar to pi, because these bonds actually are created by the overlapping. So we would see that, and I'll use a little bit lighter color purple to give us that. They would be in this area, right? So the three-dimensional aspects would look like that. And obviously, this can be shown better using computer models, but we'll show that in this last example here. And we'll use CH2O, so formaldehyde. And let's take a look at formaldehyde in our notebook. CH2O, we should be familiar with. We've seen this one before. 4 plus 1 plus 1 plus 6 equals 12. Carbon at the center, 3 bonds. oxygen, the creation of our lone pairs leaves us with this molecule, and to create octet on carbon, we find ourselves with a double bond. So now we do recognize a double bond. We should be able to then recognize that this is sp2 hybridization, which involves 2s and then the 2p, let's say Z and 2p Y, and we've left over a (2px) that is not being used on the carbon. So if we keep carbon in the center and we show the overlap, let's say we want to talk and put oxygen in the plane of the paper, we would then put hydrogen into the plane of the paper and one hydrogen out of the plane of the paper. Remember, all of this is a function of the molecular geometry. Remember, this is trigonal planar. So we should expect, based on this molecular geometry here, that this is, and again, I want to get a little specific here. This would be one axis. This would be one axis. And then there would be another axis here, right? So if we call this Z, we call this Y, and we call this X. Okay. The axes would represent kind of our position. So if we needed to draw this using the sp3 hybridization, I would show the hybridization as such. We would have one lobe into the paper. We would have one lobe coming out towards us. Okay. We would have a leftover 2p, and in this case, the 2p would be in the z-axis. So let's just switch this and let's use 2pz as the leftover. And let's say that 2px and y were used for the hybridization. All right. If we look at oxygen, and we'll use blue again, if we looked at oxygen, we see that oxygen has also sp3 hybridization, where one of the lobes is in the paper, one is coming out of the paper, and it has a leftover p orbital as well. When we're dealing with hydrogen, we should be comfortable in recognizing that hydrogen only has the s orbital. So hydrogen will be overlapping via a spherical s orbital. If we wanted to take care of our lone pairs, we should be able to recognize that oxygen's lone pairs that are not bonding are in the sp3 hybridized orbitals, and oxygen has an electron that is housed in the p orbital that is involved in bonding. Carbon has an electron that's housed in the p orbital that's bonding, and then carbon and oxygen both have an electron housed in the overlapping sigma bond, right? So this is our single bond here, sigma. We can look at it that way. We then will have a pi bond that exists and takes care of these. And now this pi bond can be above or below, right? It just can't necessarily be represented in both places, but it does exist in both places. So we have electron density here, which is our pi bond in our two-dimensional drawing. Okay, we have electron density in between the hydrogen and the carbon here, which are two other sigma bonds, right? and I should use a darker color, obviously. Two other sigma bonds, which are these bonds. And now we have represented everything, right? We have octet fulfilled on all atoms. You can count the dots, which is the number of electrons we expect to see, 2, 4, 6, 8, 10, 12. And you can see where the bonds exist, right? And this would be labeled a pi bond. So a diagram very similar to this is what I'm going to be expecting from you guys. We'll talk a little bit about the resonance structure and take a look at question 8 NO3 and its resonance structure in class. But this has been a good video to walk through the in-class worksheet. I suggest that you be very comfortable and familiar with all aspects of this as we move forward and get ready for the next assessment. Again, if you have any questions, feel free to reach out.